Assalamualaikum warahmatullahi wabarakatuh. Uh, we are, we are from Group 10. Want to discuss about the principle of movement. Okay, for the table of content, uh, we have six, which is the first one is theory, observation, discussion, result, and application in real life, and also the conclusion.
Assalamualaikum warahmatullahi wabarakatuh. I am Nur Soleha binti Muhammad Arifin with matrix number DD240079. I will present you the theory of principle of moment. The principle of moment is a fundamental concept in rotational mechanics. It is stated that for a system in equilibrium, the sum of the clockwise moments about a pivot equals the sum of anticlockwise moments. The principle of moment is crucial in mechanics and engineering because it governs rotational equilibrium and ensures stability in various systems. The mathematical equations that were used in this principle are moment equals to force multiplied by distance.
We use the 2.1 Newton for the left pivot bar F1 and right pivot bar F2. For test 1, the distance of force for left pivot bar was equal to the distance for left pivot bar from the center pivot bar. The force of F1 and F2 are equal, so the total value of moment is equal to 0. Thus, it is in equilibrium. For test 2, the F1 should be maintained and smaller than F2 because the load required for right pivot is more than left pivot to balance the pivot bar. Thus, the radius of force and distance are small. The distance of the right pivot was shorter than the distance of the left pivot.
Okay, for the discussion, for the part discussion, the first one is discuss the graph obtained. The graph shows the relationship between force and distance from the pivot based on the principle of moments, which is the moment equal to F times D, which is which is F is force and D is distance. A straight line graph indicates direct proportionality with balanced moments, confirming the theory. This demonstrates that the system was in equilibrium during the experiment. And for the second one, discuss your opinion about the summation of moment from your experiment result. The experiment showed that the total moments on both sides of the pivot were nearly equal when in equilibrium, supporting the principle of moment. Despite minor discrepancies, the results closely matched theoretical expectations. This suggests the setup was effective in demonstrating rotational equilibrium. And for the third question is if the moment is non-zero, what are the factors may influence? So if the moment is non-zero, then many factors can be inflated, which is the first one is friction at the pivot point, which can resist rotation and affect balance. And for the second one is inaccurate placement of weights or incorrect reading of distance. And for the third one, weight hook mass not accounted for properly. And the fourth one, parallax error when reading measurements on the panel. And the fifth one, non-horizontal alignment of the pivot bar affecting through moment arm length. So the all factor can lead to a small error, causing the moment not to balance perfectly.
Now let's move on to the result section of our experiment. In this experiment, we perform both different tests to investigate the relation between force, distance, and moment on both sides of the pivot bar. For each setup, we recorded the force applied F1 and F2, the perpendicular distance from the pivot D1 and A, and then calculated the moment using the formula M equal F times D. Here's a summary of the result. In figure 4.3a, both forces and distance were equal, 2.1 and at 0.16 meters, resulting in equal moment of 0.336 Newton meter on both sides. The system was in perfect equilibrium with a moment difference of 0 Newton meter. The force and the distance ratio were both 1. In the figure 4.3b, while F1 remained the same, F2 were reduced to 1.5 Newton, and the distance was 0.1 meter. This produced a clockwise moment of 0.3336 Newton meter and an anti-clockwise moment of 0.15 Newton meter, giving a difference of 0.16 Newton meter. Indicating the system was not balanced, the ratio also changed to 1.4 to 0.625. In figure 4.3, F2 was increased to 3 Newton with a distance of 0.12 meter, resulting in an anti-clockwise moment of 0.36 Newton meter, slightly more than the clockwise moment. This led to a negative difference of negative 0.024 Newton meter. Lastly, in the figure 4.3d, we apply a high force of 6 Newton at a short distance of 0.055 meter. The moment calculated here was 0.3 Newton meter, very close to the clockwise moment of 0.336 Newton meter, giving a tiny difference of 0.006 Newton meter, showing it was almost in equilibrium. We also commutated that the ratio of F1 over F2 and A over D1 for all tests, and we observed that in most cases the ratio reflected the expected proportion relation stated in the principle of moment. Overall, this result supports the theory that when the moment on both sides are balanced, the system reaches equilibrium.
For application in real life, there are 3 applications. The first one is balancing scales. Traditional scales balance when the clockwise and anti-clockwise moments are equal. When you place an object on one side, you adjust a weight on the other side to balance it. This shows how both force and distance from the pivot affect balance, a practical way to measure weight. Second, construction crane. Cranes use the principle of moments to stay stable. A counterweight on one side balances the load on the other. Engineers make sure the moments on both sides are equal to prevent tipping and ensure safety during lifting. Last but not least, seesaw. On a seesaw, 2 people can balance even with different weights by adjusting their distance from the pivot. A lighter person sits farther away to create the same moment as a heavier person sitting closer.
The conclusion of this experiment is: to conclude, the experiment effectively demonstrates the principle of moment, which states that a system is in rotational equilibrium when the sum of clockwise moments equals the sum of anti-clockwise moments about a pivot. Most of the results supported this principle, showing that when force and distance were correctly balanced, equilibrium will be achieved. Although some discrepancy occurs, they were likely due to minor experimental errors such as inaccurate measurements or difficulties in positioning the load precisely. These variations are common in practical experiments and highlight the importance of accuracy and careful setup.